All right, students, I just want to talk a little bit more about covalent bonding, okay? Covalent bonding, just to remind you, are electrons shared between two atoms to form a chemical bond. So the other things that we want to talk about today are bond order, bond length, and bond energy. Let's look at two chlorine atoms, and to do it, we're going to draw their Lewis dot symbols. Two chlorine atoms come together to form one chlorine molecule, which is why chlorine is diatomic. So as hopefully you can recall, this electron here is going to be shared with this unpaired electron here, and these two electrons will come together to form a bond between these two chlorines. So this is our shared pair of electrons. As I have talked about previously, we're not going to draw a shared pair of electrons though as dots anymore. Rather, it's best that we re-represent that like this. So looking at this, it's important for you to remember that this line just simply represents a shared pair of electrons. Let's start by going back to the top and defining some of these terms. What is bond order? So bond order is the number of shared pairs. So if we come back down here to this bond, we would say that its bond order, what we might usually write as BO, is 1. So if we have a bond order that is 1, this is what we call a single bond. The term single means that there is one single shared pair of electrons that form the bond. So bond length is the average distance between the nuclei. So bond energy is the energy needed to break the bond. Now let's think about two oxygens. So in the case of two oxygens, let's again do their Lewis symbols. As you can see, there are two lone electrons or unshared electrons on the Lewis symbol for each oxygen. So to get to their valence of 8 electrons through sharing, these two oxygens can do something pretty remarkable. They are going to be able to share these electrons, but they're also going to be able to share those electrons too. What would that look like? Looks like this. As before, these electrons here in the middle are being shared by both oxygens. So both oxygens now have 8 valence electrons. Again, that should always happen. Notice 8 electrons, 8 electrons. How do we describe this bond? Well, it would look something like this. Notice in this case I've written 2 lines. Why have I written 2 lines? It's because we now have a bond order of 2. This is what we're going to call a double bond, and each line represents a shared pair of electrons. Now, one fundamental thing that I cannot say enough is that this, even though it has a bond order of 2 and there are 2 lines, this is not 2 bonds, and this is not 2 single bonds. This is a bond that happens to share 4 electrons or 2 shared pairs of electrons. So when we come back up here, we call this bond order of 2, this is what we call the double bond. So to be clear, that double doesn't mean there are 2 bonds. It means that it has a bond order of 2, but the double bond is still a bond. It just is made up of 2 shared pairs of electrons. So again, it is a bond. So what about bond energy or bond length? As it turns out, the force of attraction between these shared pairs and the other nuclei are much greater. So in terms of a single bond is going to be slightly longer than that of a double bond. Now, because it's involving more particles, we have more forces of attraction. It means we have a greater bond energy. And so we would say then that a single versus a single bond is actually weaker than a double bond. It's easier to break. Okay? Let's look at one more example. And so we're going to look at the Lewis symbols of 2 nitrogen atoms. Here are the Lewis symbols for 2 nitrogen atoms. As we've before mentioned, they're going to share electrons until they've achieved their valence of 8. But nitrogen does something pretty remarkable. Nitrogen can share those electrons, and those electrons together. And I'm sure if you're following this pattern, you've put it together and you can see, so this is what we're going to get. So this is a molecule of nitrogen. And notice this time we have a bond order of 3. A bond order of 3, students, is what we call a triple bond. So students, this is not 3 bonds. This is not 3 single bonds. This is still just a bond. One. This is one bond. This one bond happens to possess 3 shared pairs of electrons, but it is still just a bond and not 3 bonds together. Remember, each line represents a shared pair in the bond. If we're involving more electrons, then I'm sure you can imagine the forces of attraction are even greater this time. And so now the greatest or highest energy bonds are your triple bonds. But because they're highest in energy, that means that these nuclei are getting attracted to the shared pair even greater, which is bringing down the distance even further, which means that a triple bond, even though it's got the largest bond energy, its bond length, it happens to be the shortest. So again, bond order, number of shared pairs of electrons. If it's a bond order of 1, we call it a single, 2 is double, and 3 is triple. Bond length is the average distance between the nuclei. Singles are your largest in length. Doubles are in between a single and a triple is your smallest length bond. And then in terms of bond energy, your single is your weakest bond, followed by the double, and then the triple is the strongest bond.